Okay, this is a new seminar. I think I got Goldbach. I think I proved it. I think I showed it's correct. The induction proof, the second one at Vixra, I don't think it'll be acceptable to a lot. And it's right at the psychological point where I don't want to go back and look at it because I'm afraid I'll find it counterexample or it doesn't work. And I'm having a pleasure with the illusion that it definitely does work. And I have enough evidence or, reflection on it that it seems like it does work. Perhaps better proof of Goldbach is correct. Involves symmetries a little bit more. I might go for another paper on Vixra called Goldbach and Symmetries, something like that. I believe there's a clear case that if you take the inverse linear functions, you'd have to read the first paper there, then you find symmetries in a list of the top row and bottom row entries where the evaluation of the inverse functions at a point in the bottom row generates all rational numbers, indicating it's a prime. And then if you get one of those down here, it's for sure you'll get one in the second row, indicating another prime, indicating two primes exists, the sum of which is 2n. So it looks like that you have a guarantee of primes less than the square root of 2n. And then between 0 and n, do you have a guarantee of other primes? Is that Bertrand's postulate? Is pretty easy to establish. If that's true, then that other prime will generate with these inverse functions all non-rational images, and it'll mirror one upstairs from it, implying it's also prime upstairs, and voila, you have it. That one's more work, I think, and it looks better. It's more work. The other one, the induction proof, is way too fast. Okay, but this second seminar that I'm working on is to do Galois theory, and I'll memorialize it a little bit right now. So here's a book that got me into this. Richard Foote, writer of a tome on abstract algebra, emeritus of, I think, Vermont University or some place in Vermont. I think he recommended this book to me, and he was right on. I didn't, think about it too much, but later I did buy this book, and I'm looking at it, and I see he could understand that I have certain weaknesses in mathematics and other things, and this book, being less abstract, can help me through those weaknesses better than other books. I like pleasure spasms right away, and wading through Herstein or McLean, Sanders McLean or Foote or other books just doesn't deliver it fast enough. This one, by design, I think does. He doesn't get too abstract. He says as much in his introduction. I've emailed Charles Robert Hadlock, who's been kind enough to email me back, and I think it's pretty clear that he wants to go slowly with problems which are solved in the back, which is also helpful. So, at any rate, this book, I think of all the ones I've seen, is by far and away the best for me. That said, it's still a little, too dense. He gets into such proofs that are, a little bit longish. Here's all these are equivalent, and it goes on, for a page or two, and it seems, maybe I can wade through all this. And here he makes, just take a moment here. What I think is a little awkwardness if he, should watch this. R equals a bunch of stuff with commas. I think he really means R is an element of these, conjugates. Roots are called conjugates. And this, drives me kind of crazy here. So occasionally it, relative to my way of thinking, kind of gets blurry. And, these Keras mathematical monographs are not subjected to, 15 editors and, 15 editions, as are some, intermediate algebra textbooks and calculus books. So it will have some awkwardness is in it. There's one problem I did manage to solve, that he says something is obvious, and I worked on it for a few days. It's like exaggeration there. And indeed, it came forth as obvious eventually. And that one is right here on page 65. It's important to realize that the above theorem only gives sufficient conditions. He's talking about Eisenstein's irreducibility criterion, which I think I understood. That's a nice, sweet proof, not too long. Sufficient only condition for irreducibility over Q, for example, enables us to conclude that x to the fifth minus 2 and this thing are irreducible over Q. Take p equals 2 and 7. So a little fill in there. 2 does not divide 1, the coefficient of x to the fifth. 2 does divide the constant term, but 2 squared does not divide the constant term. Ergo, using Eisenstein's irreducibility criteria, you can say that is irreducible over the field of Q, rational numbers. And the second one, 7 doesn't divide the leading coefficient. 7 does divide the constant, but 7 squared does not. 7 divides all other coefficients. Therefore, this is irreducible. Then it goes on here, but it does not give us any immediate information about x cubed minus 3x minus 1 or x to the fourth plus x cubed, blah, 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 but both of which are also irreducible over Q. So it finds some, but it doesn't find all. It's sufficient, but not necessary. I think I have that right. To treat a situation like these, sometimes a simple change of variable can be found to put a polynomial in a form to which the theorem is applicable. For example, making the change of variables, x equals u plus 1, you put that into here, and you'll obtain u cubed plus 3u squared minus 3. And that one, 3 doesn't divide the leading coefficient. 3 does divide the constant, but 3 squared does not, so this is irreducible. Now, here's where I managed to do something. Very proud of myself. Managed to fill in one thing here. We obtained this, which is now seen to be irreducible using p equals 3. Clearly, the property of irreducibility is not changed by this transformation. Question mark, in my estimation, that could have been made into a problem at the end of this section to show this, or to at least argue it. Here is an argument for that, and then we'll get into a few other things. So I make this substitution, and I get u plus 1 cubed minus 3 times u plus 1 minus 1. That into that gives that. This one is, remembering the binomial theorem, I think 3u squared maybe, going down with these powers, the other power going up, the other number being 1, so I just get this, and then another one of these to the first power plus 1, using the Pascal's triangle there for these coefficients, minus 3u minus 3 minus 1. And that goes out, that goes out, and we're left with u cubed plus 3u squared minus 3, which is what he got, and that is irreducible per Eisenstein. Now, if this is irreducible, then this one is too, and vice versa. That would be a if and only if. I think the way to show this, to see this, note that if I had u minus a times u minus b times u minus c, it is reducible to this if then I substitute back in here x, which I use a little algebra here, and I get u equals x minus 1. I substitute that in, and I get it's reduced, and it's reducible. I think this would go both ways, and I think that's a, is that a proof for the third case, but it's obvious for any cases that would be true. So I did manage to, fill in one thing for Hadlock. Don't need, a check for half your royalties at this point. Speaking of which, there's some chance that Charles Robert may join my class. And I thought in the next video, I would go over some of the rules and regulations if he should decide to join us. And I'll start to give a gloss on, I guess we call it Galois theory. I think a better name for it is an abbreviation I came up with here. No quadratic formulas for degree 5 and more. It's quite a mouthful, but that's the ultimate idea, to show that you cannot get a quadratic formula-like thing for general quintics. I think that's 5 quartic, it's 4 quintics and beyond, or